Nonlinear static buckling of reinforced concrete frames. Abstract. The purpose of this paper is to study nonlinear static buckling of the reinforced concrete frames, through studying geometric and material nonlinearity. Both physical and mathematic models of eigenvalue and nonlinear buckling analysis were established. The main objective of the study is the determination of the critical buckling loads and generation of the complete force deformation behavior of such structures within a specified load range, based on the use of a computer program developed for this purpose by using MATLAB program. The general approach to the solution of the problem is based on the finite element method and incremental numerical solution techniques. Also, the finite element analysis software ANSYS was used to the determination of the critical buckling loads and generation of the force deformation behavior of such structures. The results obtained from the analysis above were compared with experimental published results, the American Standard, ACI 318, and the European Standard, CEB, showed reasonable and acceptable with the computer program and ANSYS software results. Keywords: nonlinear buckling analysis, eigenvalue buckling analysis, reinforced concrete frames, finite element. 1. Introduction. Calculating the stability of structures has always been an important engineering discipline. Especially the calculation of the critical buckling load of a structure has been a subject for study since Leonard Euler in 1744 calculated the critical buckling load for a simply supported column. Buckling is a phenomenon where a structure suddenly changes from one equilibrium configuration to another equilibrium configuration. The calculation of buckling loads of a structure is of great importance, due to the possibility of sudden failure of the structure, if the critical buckling load is reached. Some structures might lose all stability when the buckling load is reached, which could put people at risk, if a roof or other similar structures loses all stability. Many researchers have studied finite element method and nonlinear analysis of structures. Some of these studies will be cited here. Wood and Zienkiewicz, 1977, presented a continuum approach for the geometrically nonlinear analysis of oriented bodies E.G. beams, frames, and arches in total Lagrangian coordinate system using finite element method. The nonlinear equilibrium equations are solved using the Newton-Raphson method, for which a number of examples were solved. The derivations were extended to include axisymmetric structures. W.A.M. Alwies and T. Yosemite, 1978, presented a finite element formulation to determine the elastic lateral torsional buckling load of braced and unbraced planar structures through a series of equilibrium states at incremental steps of in-plane loadings. Chages and Churchill, 1987, presented the basic concepts involved in the construction of load deflection curves for geometrically nonlinear system by the finite element method. Cam, 1988, presented a general method for the large deflection analysis of inelastic plane frames. Chen, 1988, presented a geometric and material nonlinear analysis procedure for framed structures, using a solution algorithm of minimized residual displacements. Kasimali and Abbasnia, 1991, suggested a method for large deformation and stability analysis of elastic space frames. K.W. Wang and R.F. Warner, 1997, presented an efficient approach for the nonlinear analysis of reinforced concrete frame using line elements. Zdenek Pibasant and Yuyan Xiang, 1997, proposed an improved method of analysis of reinforced concrete columns in braced, no-sway, frames, which was suitable as a simple computer solution for design practice and was more realistic than the existing ACI and CEB methods. Endradula CSKA, 2007, discussed the approximate determination of the elastic plastic load parameter of structure, and he also established a lower and an upper bound for the critical failure load parameter, with the aid of which the results of computer calculations can be checked. Rafat Sezer, 2010, studied the geometrical nonlinear analysis of the prismatic plane frames with stiffness matrix method by using the stability functions. K. Azaros, E. S. Mistakidis, 2011, presented a method for calculating the buckling loads and the buckling shapes of continuous beams with unilateral intermediate constraints based on the theory of elastic stability using the Euler equilibrium method. The purpose of the study was to find the critical load or buckling load of the reinforced concrete frames. 2. Methodology. To predict buckling loads and load deformation curves of reinforced concrete frames, the methodology will be prepared through the following steps. Different finite element approaches have been proposed for the analysis of different types of structures. The theoretical study depends on nonlinear static buckling of plane frames. The Newton-Raphson approach will be utilized to trace the equilibrium path during the load deformation response. About 3 models, 1 single reinforced concrete column and 2 reinforced concrete frames, will be prepared. Loading should be applied to the plane frames until the failure occurred. The mode of failure characterized by flexural failure of concrete. Load deflection curves will be plotted for each model and compared to predicted ultimate loads. The experimental results of plane frame models subjected to transverse load will be utilized for calibration of the finite element models using structural program, ANSYS. The analysis will be carried for nonlinear static buckling and different buckling modes will be resulted. The comparison of results will be done for the experimental models and mathematical models using software program, MATLAB, and 2 different code of practice, ACI, CEB. 3. Results and discussion. The results obtained for linear and nonlinear buckling analysis for reinforced concrete models will be presented according to the following. 1. Buckling load factors and buckling mode shapes. 2. Load and deformation relationship. 3. Elastic modulus change with different codes and experiments. 4. Buckling loads calculated with elastic modulus obtained from different design codes, experiment, MATLAB, and ANSYS program. 3.2 Load and deformation relationship. 3.3 Elastic modulus change with different codes and experiments. 3.4 Buckling loads calculated with elastic modulus obtained from different design codes, experiment, MATLAB, and ANSYS program. 3.1 Buckling load factors and buckling mode shapes. Table, 3 Buckling mode and buckling load factor. Buckling mode No. Buckling load factor, N. Tables, 3, 4, 5, show the buckling load values and figures, 3, 4, 5, 6, 7, 8, 9, 10, 11, show the buckling modes which represent the shape a structure assumed under buckling load, elastic formulation. Buckling mode No. Buckling low. 4. Conclusion. The discussion of the results of the analysis obtained in this study resulted in the following conclusions. 1. The eigenvalue buckling loads and the buckling modes for various reinforced concrete frames were presented using ANSYS computer program. 2. Nonlinear buckling analysis program by using MATLAB was used to compute the buckling load utilizing the stability functions to determine the buckling load. Comparison with ANSYS program results showed little differences in their values. 3. The buckling load value is strongly dependent on the choice of modulus of elasticity that is known material uncertainly. Nonlinearity of material, concrete, is assumed to be presented by concrete average strength and lower value of modulus of elasticity, see Figure 6.26, Figure 6.31. Under this assumption the results obtained showed very little differences in the values between MATLAB, ANSYS, ACI, and CEB and published experimental works in buckling loads in structural members and frames of reinforced concrete.